Welcome one and all. If you are having any technical interviews that you are preparing for, this is the place for you. So the idea is we're going to go over the problem. I'll give you some time to work on it on your own, and then we'll come back for my solution. So if this is the kind of format you like, remember to like, subscribe, all the good stuff. All right, here we go. This is contacts. We're going to make our contacts application. The application must perform two types of operations. You can add a name where the name is a string denoting a contact name, and this must store the name as a new contact in the application. The second operation is to find a partial, where partial is a string denoting a partial name to search the application for. It must count the number of contacts starting with that partial string. So we're told that the constraints are n is up to 10 to the 5th, which is actually not that big. And the size of a name string is 21 at most, and the partial could also be 21. It is guaranteed that name and partial contain only lowercase English letters, and the input doesn't have any duplicate names. All right, so here's an example. So if you add hack and you add HackerRank, those are two separate words effectively. And if you do find hack, HAC, that should find both of these. HAC is the beginning of both of these, so you should get 1 and 2 as your output for that. And then finding HAK will return 0 because there's no HAK here. I'm going to give you some time to work on it. I have the link to this in the description, so take some time and we'll come back with my solution afterwards. All right, we're back, and here is how I approach this solution. It is actually one of my favorite data structures. It's called the try, and it is a very compact way of storing a lot of information, especially with strings, so it's very appropriate for this particular problem. And what I ended up doing was creating my own data structure in JavaScript, so I'll go over that in a bit, but I want to go through my process first. So the idea here is I'm going to have a try that is stored, and this is, again, a data structure, and I'll have my output, which is going to be the array that I will output in the end. And then basically I loop through all the queries, and so for each command that's an add, I just add the string to the growing try, and then otherwise it's going to be the partial, and then I will basically push to my output array the match count that I'm getting from my try. So we'll go into what that looks like, but in the end I'm spitting out basically an array of just numbers. All right, I want to go over the basic node structure before I talk about the try, which kind of like sits on top of the node structure. So the first thing is that the node is very basic. It just stores the character, and then it keeps track of its children. So if you think of the children as one letter and a string of characters, effectively, that the children is all children that occur afterwards. And I'll show a diagram of this afterwards. So this ends is kind of like one of the keys to making this super efficient. .ends is just a running count of the number of words that are basically passed through this node. So whenever you're creating a new word in your try, you have to like kind of like go over previous nodes, and every time you do that, it's basically like a new word that's being created. So there's a new end that would be associated with that particular character, and so that you can keep track of that, and that will be effectively the count of ends for that particular node. So that'll help with the partials later. Here I have some basic functionality for a node. It just makes sense, I thought, to have the node have the functionality of handling its own children. So here is a find or create child, which will increment the ends, because again, anytime you're going over a node, that means that you're creating a new word. And I have a find and create method here that is pretty straightforward. Just create a new node with the character, you push it, and then you return that child. And then here is the same thing with just finding it, where you will use the .find method that is part of arrays, so it's an array method, and it will return undefined if the character is not found. So here in my find or create, what I do is I try to find it, and if that's null, I do or and then create the child, and then I'm returning that that new child node. All right, for the try itself, with any try, I kind of start with a root node that's pretty blank, and I kind of want to showcase this in a diagram. So the idea here is you'll have a let me see, yes, or like a root node. So you have a root node that basically doesn't do anything. It just stores children, and it can have its children. So let's say we have the word hack. You go to the root and you say, okay, do you have any children? the answer is basically no to start out, so it will start with an H. And then H will create another one that is an A, and then you have a C and a K. I'm kind of running out of space here, but you get the idea here. And so if you added another word like hat, for example, you would go to the root, you'd see the H is already there, the A is already there, but there's no T, so you'd create another branch here as the T, and this would spell, you know, hat like that. And so you could basically keep adding to this. One caveat here is that I will need a way of denoting the end of a word. This is actually good practice. So what I'm actually ending up doing is creating another node here at the end, which is kind of like an end node. There are a few ways that you can implement this. You can create another node that's like a end node data structure, but in this case I just create another character that's like a star, and that star will denote the end of the word. This is just good practice, and there was only one test case where this strategy fails, and it's because I don't have that implemented. So I had to implement this just for that one test case, but other than that, it was, you know, that's pretty standard practice, to be honest. Okay, so that's the idea. When I add a word, I basically just iterate through that word and I create a new character. But what I'm doing here is I start with the root as my current node, and then I will use find or create child to get the next node effectively, and I just keep doing that over and over again. And at the very, very end, I do find or create because I want to increment that one end by adding a end character here. So here I have a special character. You can kind of make this whatever you want, and it's just really good practice to make that a constant that's part of the class. There was one test that kind of required keeping track of the end, and that's why I had to include this one little line here. But it's also just good practice for a try to have a end, something to denote the end. Okay, here is where we actually return the counts, and so this is actually pretty straightforward also, and it's super simplified just because I'm keeping track of the ends for each node through the process of adding. So where I do get match count, I get the partial, I start with my root node, and then I will loop through every character in the partial, and basically I just do a find child, and I don't want to find or create, I just want to find the child for that character. This will return undefined, or if it doesn't find it. And so that's where I can do like a short circuit here, where if there's anything in the partial that's not found, then I just return 0 because it's not found. Otherwise, I just kind of reuse that child node. And in the very end, when this loop finishes, the partial will have ended at the last node, and that last node is basically saying, okay, anything after me, they are all valid words, but because I've been keeping track of all those ends for that node, I can just return the dot ends. And this is effectively like constant time doing this lookup. Going through each character of the partial is like big O of k, but because we're told up top that k is at most 21 here, that partial is 21, it's pretty insignificant. So that is how this solution runs down. So if I look at the big O notation here, for each query that comes in, I'm looking at, so you have big O of n, and then k is the length of the word, the partial, sorry, not the partial, the string, the name. So however long that is how long it takes to navigate through it. So that's, if I look at my picture again, so basically like the length of this word is how long it takes to get to that end. So it's not that long. It's, again, 21 at most. So that's that. This get match count is very similar. Again, I have to like navigate the partial. Once I get to the end, it's basically constant time. So once I get to this k, it's sort of like this times 1 effectively, where that 1 is just looking at the dot ends. So in the end, you're basically looking at big O of n times k. I should say that this is like maybe times times 2 technically, but that simplifies to just big O of n times k. If you want to smudge the lines a little bit and say that k is pretty insignificant, you can say this is kind of like big O of n, but that's not technically what's happening. All right, so let's see this sucker run. Let's run some code. All right, so that runs on this sample. Let's submit some code. And sure enough, it works on that as well. So I hope this has been helpful. If this is the kind of format that you like, let me know with the like, subscribe, comment, all the good stuff, and I will see you in the next video.